started to be so cosmologist, but now I'm just working on the three-body dynamics, and so I found it quite fun. And so when just I visited to these places, I was asked by many people that this is your, so how many times have you visited so Taiwan? So I tried to just check it, but unfortunately I was not able to find my first visit. So this is my record of visits in this century. So this is 2001 and 2002 and 2011 and 2012. So this is actually, so this visit, last visit, I was very surprised. It is more than 10 years ago. Yetting just invited me to give a talk here. So this is, I already started to work on the planet. So I just divided it to just in two different talks. So this is cosmology, and so this is astrobiology or related to exoplanet. So this is a talk that I gave 10 years ago to my surprise. So now, I'm just talk about, I'm just started a little bit from the many body system to few body system dynamics, and from cosmology and exoplanet. Now I'm going to the sort of limit of three body, because two body, so this is analytical solvable, so there is no nothing to work on the sort of two body if this is a really point particles. But today I'll just give you some flavor of the sort of three body dynamics, and so this is a theoretical framework to how to just to sort of compute the dynamics of three bodies, so secure perturbation theory. So my aim, my purpose is to what extent we can just find the black hole in triple system. As you know, gravitational waves, they found the sort of binary black holes. But so this is really limited in the very final epoch of the merging of two black holes. But in optical, in other band, so there should be much sort of wide separation, wide variety of black hole binaries, but it is far from emitting any gravitational wave, so we cannot see it. However, if some small fraction of them form a triple system, then so tertiary star or some tertiary pulsar or whatever, we can just in principle observe it. So from the motion, very detailed motion of the tertiary star, we may be able to identify the possible existence of the inner binary black hole. So that is basically what I'm going to tell you today. So first, I will start with three-body dynamics or the new problem. Maybe I don't have to tell you, because if you just get a sort of class in physics, you should know a lot of very sort of famous mathematicians working with three-body. So therefore, you have a lot of special functions after their name. So what I really realized, only a few years ago, I just started work on three-body dynamics. Then suppose if quantum theory and relativity are not being discovered, three-body problem could have been still the frontier in mathematical physics, even now. So this is my really conclusion. But because of the, so I can sort of rephrase it. So it could be a superstring theory before the 20th century. So this is evidence, because all those great mathematicians, you know, they really work on three-body problem very seriously. And as a result, it is quite unfortunate. And now, I cannot work anything beyond this, because of their genius. So all the things I could do are two pieces. One, fortunately, observation, they really continue to discover amazing variety of three-body systems. Even that genius cannot imagine it. So this is one thing. Another thing is computers. Now we have really sort of wonderful computers, even in Macintosh, MacBook or something. Maybe they can just do a very accurate numerical simulation. Even such genius cannot do it. So therefore, the only way, the niche or the space that I can just work on is using numerical simulation or three-body simulation, and to apply it to a quite interesting three-body system that these people cannot imagine. So this is a sort of example, ubiquity of triple system in astronomy. Of course, this has been known for a while. If you just consider stellar system, actually significant fraction of massive stars are formed in multiples. So more than 70% of OBA stars are multiples, including binary, not only the triple, but more than 50% of these stars are the binary multiple system. Of course, our nearest neighbor, Alpha Centauri, is a triple system. And so this is something that, so that the genius cannot imagine it. now we have many exoplanets. So this planet, some fraction of planet form in the binary star system, and we have multiple system, or even, so this is not yet discovered, but definitely this is an exomoon or so satellite. So this is a really abundant, quite interesting, and sort of three-body system that we could really apply it. And in addition, so this is quite early, already 10 years ago or something, but we know that so our universe is dominated by binary black holes. So this is, in order to have the total calculus for the binary black hole, some fraction of them should come through the triple dynamics. Because of triple dynamics or something like this, they will have that much sort of going to accelerate the margin of binary black holes. And indeed, so this is some example. This is a real example, triple of compact object. So I think, I don't know to what extent you know it, but some radio people should know it. This is really amazing, interesting system. This is a pulsar white dwarf binary system. And so this is orbited by the tertiary white dwarf. This is discovered in 2014. So this is really wonderful. So this is a sort of end of the introduction. Again, so you know, so this is a three-body is a quite wonderful novel. I learned about. Actually, this first book is very well written. So this is studied cosmic microwave background. So maybe the author, this author I think should come from the engineering department or something like this. But they should know a very nice cosmology or something. So that I'm quite impressed. Becoming less and less impressed, but this is quite nice. Apart from this, so this is again in the famous movie Carl Sagan said Alpha Centauri was a triple system, two suns tightly orbiting one another, and the third more remote circulating them both. What would it be to be like to live on a world with three suns in the sky? So this is really motivation. And actually, I thought maybe 5 years ago or something, the tertiary of Alpha Centauri, Proxima, was discovered to have a planet actually. So of course, I don't know, so they have really life or intelligent life there, but still, so this, his imagination is really close to the reality. So this is my introduction. And again, first, very important thing, the gravitational triples are generically unstable. So this is some kind of diagram for the stability boundaries. So this is very famous work by Marvin and Arces more than 20 years ago. They just make a sort of find a stability boundary of triples. Basically, if you have a very tight binaries, and tertiary is very widely just orbiting them. So this is stable, because so basically there's no interaction between the inner orbit and outer orbit. But if these two orbits become closer and closer, it started to be unstable. So this y-axis is basically the ratio of the outer semi-major axis and inner semi-major axis. But the interaction happens preferentially around the periaxion. So therefore, instead of taking the outer semi-major axis, they take outer semi-major axis correction for the eccentricity. So this y-axis is some kind of measure of stability, and right axis is the eccentricity, it's outer eccentricity. So after some kind of combination of semi-analytical model and numerical simulation, they found basically this above this region, so this is stable. Basically, inner and outer orbit is far away. But in this region, so this is very unstable. So eventually, it could be just go away. One of those people will go away from the system. You are left with these two. Actually, so this is really related to one formation channel for the photodigital in exoplanetary system. But so this is not a sort of today's topic. And so this is a sort of schematic diagnosis of the system. But so this kind of instability is quite generic in a sense, because so this is really come to the hierarchical structure in our nature. For example, we know that in particle physics or biological system, astronomical system, even so the social system, we have a quite distinct hierarchical system. So if everything is just in one unit, so this is unstable. For example, if you just take some class of professors, if you are completely equal student and professor, student never listen to professors, right? So this is everything chaotic. So you are so educated so that you should at least pretend to respect professors. Therefore, that I can just teach you that quantum mechanics or something like this. Okay. So this is the same thing, but in the cork and lepton, atom, molecule, DNA, cells, organs, animals, village, cities, nation, blah 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 blah. Everything. So this is really dictated by some kind of sort of huge difference of the interaction. Therefore, actually, so the stable tuple system is one of them. So this is, in the case of if I focus on the gravitational three-body system, even in such very simple system, quite non-intuitive dynamical behavior happens. So one of the sort of very good example is ZKL effect. In Japanese, we call it Kozai effect. Because of Professor Kozai just worked out this kind of three-body, non-trivial three-body dynamics. I will just give you an example there. That before that, so this is a quite amazing to me, sort of real system, already observed system. This is a millisecond pulsar in a triple system. So this is the sort of triple system. So this is the inner binary. Inner binary consists of the pulsar and white dwarf. And so this is zooming. This inner binary is orbital period is 1.6 days. So this is the pulsar, and so this is white dwarf. But this binary system is orbited by the tertiary white dwarf. And so orbital period of white dwarf is about 1 year. So this is quite interesting. And in addition, because that one of the cell component is pulsar, you can just make a very precise measurement of the arrival time. Then you can just work out the architecture of triple system very, very accurately. If you just observe the outer Kepler motion of the outer white dwarf, so this is something like this. This is observed physics. But again, due to the inner binary, one of the inner binary is from the pulsar, you can really make a precise measurement of this region. So basically, y-axis is pulsar arrival time. Then so this is zoom up. Then so this region is really of this kind of modulation. This modulation is due to the back reaction from the inner binaries. So this is really amazing, but very beautiful. And if you try to model it, just a simple superposition of two binaries without interacting with inner and outer, it is a residual is something like this. But if you properly take into account of interaction between inner and outer orbit, residual becomes something like this. Then from this fitting, from the three-body dynamics and real observation, you got this number. This is an inner orbital period. This is 1.62 blah 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 days. Outer period something like this. And pulsar spin period is something like this. Maybe this is not so surprising for people who just do pulsar timing or something. But because this is really three-body system, quite amazingly, mutual orbital inclination between the inner and outer orbit, they can just measure 0.012 degrees. In relation to this precision, amazingly, this is coplanar. I don't know why. This is really coplanar, amazing coplanar system. And so they, I forgot something. This is eccentricity something, but this is also amazingly circular system. This might have some indication, some implication for the formation mechanism. So I don't know, actually, so what kind of the progenitor can just read this. But this is fact. This is really observed. So what I really doing is maybe this similar system should exist. But in this case, inner binary is binary black hole. So therefore, you cannot measure. But if outer, so tertiary is some stars or pulsar, then exactly the same thing that you can just apply. Then we can just really infer the binarity of the unseen companion in the central region. So this is my purpose. That before going to so that kind of analysis, I'll give you some flavor of the three-body dynamics, the secular approximation. Because in this case, so if this is really far away case, so this is stable case, basically you can just simply superpose the two Kepler motion. So this, you cannot do anything. You don't have to do anything. However, if these two is somehow sort of close, then you have to consider the interaction between the inner and outer orbit. But if you try to just do it in numerical simulation, for example, orbital period of inner and outer could be about 100 times or even 300 or 1,000 times different. So in numerical simulation, you need a very, very, very small time space. So therefore, you cannot evolve the system at all. So one very popular approximation is you will just have some, instead of the location of the planet, location of any bodies, you can really consider the trajectory of the orbit of the ship, and you will just time average over the location of the orbit, of the of the bodies. So, in a sense, in very simple cases, you consider the three-body point particle dynamics, but you can just really replace it to the two orbit limb-limb interaction. And by doing that, you can have a significant sort of speed up of the computation. So this is a very well sort of popular secular approximation in these cases. Maybe I will just do, again, so this is, actually this is not important in my sort of following talk, but I just to give you some flavor how people just work on three-body dynamics. Then you can just have the three-body sort of Hamiltonian of the three bodies. So basically, so this is a Hamiltonian for the inner binaries. This is the Hamiltonian of the outer binaries. In this case, the central object is not separate. So this is just the total mass of the inner binaries. Then so left of the part, so you can just expand total Hamiltonian in units of the same major axis of the two orbits. So in a sense, you can just expand it in the Legendre polynomial like this. If you like, you can just do it infinitely. So this term is corresponds to the coupling constant. And so at this point, this R is time dependent. But so you can just really assume the Keplerian motion and take the orbit average of the inner and outer orbit. And so this is a very powerful methodology, but in doing that, many people use it. But in this case, they assume this same major axis of the inner and outer is constant. So in a sense, they assume energy is separately conserved. So in this treatment, they simply consider the angular momentum exchange between the inner and outer. So this is a fundamental limitation of this kind of thing. But so this is very well developed. And so this is a expansion depending on the accuracy you need. You can stop at a quadruple moment, or so up to the octopole or something like that. You can just do it infinitely. So this is a standard secure perturbation. So very well known result. So this is a double average implies we will just make an average of the motion or location or phase of the inner orbit and the outer orbit. Both is averages. Then you are left with up to quadruple order. So this is a result. This is the result. And if you like, you can just compute the higher order up to octopole. So this is something like this. So in this case, the variety of some coefficient. But in any case, by doing that, you can do some kind of analytic estimate of what's going on. So this one of the very, very famous effects. So this is very popular in three-body dynamics and also recent exoplanetary dynamics is Kozai effect. And but Kozai is a professor or former director of National Astronomical Observatory in Japan. And but some people, so this first paper is a very amazingly well documented sort of review of this Kozai oscillation. Okay, thank you. Also, so the author, so the Japanese, they are quite sort of serious person. So they just find out. So this basically the same. In this community, they know the Lidov, the Russian astronomer, find out the same effects almost simultaneously with Professor Kozai. So we just call it Kozai-Lidov or something, Lidov-Kozai or something like this. But these for Japanese say, no, in 1910, this person basically find out so this kind of some effect. So he should say that, okay, then completely chronological order or alphabetic, this should be called ZLK or something like this. But in any case, so please sort of forgive me if sometimes I may call Kozai effect, but this is equivalent to ZLK. Okay, I have no other bad intention. What is a quite sort of interesting, I think quite non-intuitive effect of Kozai effect or ZKL effect or something like this. If one of the inner part binary is a TESS particle, and so outer orbit is approximated by circular, then so this is axisymmetric potential. Then in the axisymmetric potential, total angular momentum of the inner angular momentum or z-axis is conserved. So this is a conserved quantity. So this is the inclination of orbit, of the inner orbit. So this is the inner eccentricity. So this quantity is conserved in this approximation. In this case, even if you start with the circular orbit, but if the inclination or orbit of the inner and outer is a little bit inclined, then after the evolution, this E1 and I inclination is start to oscillate. So this is the maximum eccentricity they can just achieve. And in order to set in this kind of significant oscillation, they have the critical eccentricity inclination angle. This is basically more than 40 degrees. So if it is started to be a little bit inclined, so this is show a small amplitude of inclination and eccentricity. But if it is more than 40 degrees at some initial condition, then this is a very nonlinear oscillation. And in this case, sometimes this E1 close to unity. This gives a very sort of interesting diversity of the system. And as I said, so this is one of the formation channels to form hot Jupiter in exoplanet. I did not discuss it yesterday, but so this is a very fundamental case. So this is give you some example. So this is a so Tripoli system. X-axis is the time. This is just evolution. This is an inclination angle. So this is eccentricity of inner particle, inner orbit. So this is in the approximate quadruple level. So this is conserved quantity. So if you do a TESS particle plus quadruple approximation, this is of course by definition constant. But in this case, eccentricity and inclination really just oscillate. And so this is anti-phase. But if you do the full quadruple movement, in this case, this quantity is not strictly conserved anymore, but you see a much more so significant oscillation or variation inclination. And if you just include the octapole effect or so much more sort of significant initial inclination, so this is the cases. And if you set initially the orbit is orthogonal, so this will be something like this. Or sometimes, even if you start with the so saying parallel or flow-blade rotation, due to the exchange of angular momentum, sometimes it starts with flip. So the sense of rotation is really reversed in some cases. So this is completely intuitive, at least to me. But so this is again, you can just easily imagine. So this can just give a really sort of amazing variety of observed system, because so this is a very well standard sort of physics based on dynamics. But in any case, so this is some kind of background of the dynamical background. So I'll just give you some kind of astronomical background I'm interested in. Again, now we know that more than maybe 100-ish binary black hole system exist in our universe, not in our galaxy, okay, but in distant universe. So they emit gravitational wave. So we can just think about what is a progenitor, and nobody knows. So this is a variety of formation channel. But if really, so this starts from any system, I expect just before the merger, so the instant of merger, there should be some moment. These two black holes is widely separated. So in astrophysical cases, this could be a massive star or something like this. And in primordial black hole binary, that's Professor Sasaki is also expert, world expert, who also advocates that kind of case. Even in these cases, if you have a very, very tight binary, maybe significantly more fraction of this primary binary pair should be in a widely orbited. So this is my assumption, and I think so this is quite plausible. But in addition, so if this is a really black hole binary, and so this does not emit gravitational wave, nobody knows. Even though our galaxy is really dominated by a single black hole, we don't know, right? It is according to our theory, we expect our galaxy hosts about 10 to 7 or even 10 to 8 single black hole. But we cannot see unless this is in binary system. So similarly, I don't know what is the fraction of these binary black hole system exists in our galaxy. It could be 1 or 10 or 100 or something like this. Nevertheless, we cannot observe it. So assume so this could form in the sort of triple, then definitely we can just observe it exactly as the three compact triple systems as shown. Indeed, there are already some attempts to identify star black hole binaries. Okay? This is star black hole binaries. In Gaia mission, they already just identified several candidates for star black hole binaries. And in TESS mission, so this is an exoplanet transiting through surface. But using some gravitational lensing or something magnification, some people claim in some cases they might find out the one of the accompanying object is compact object or black hole. So they estimate maybe eventually from TESS mission they might find out this kind of binary, and so this person say something like this. I don't know to what extent this is believable now. However, it is certain many people very seriously looking for star binary black hole. So I'm just really waiting for that discovery. So if they just say, then I will ask the question, to what extent are you really sure central object is single black hole? Why you don't think that it is a binary black hole? So that is what I'm working on. Already, so this there are two, maybe more than that, but very famous two examples of Gaia black hole star binary system. This is a Gaia black hole one. This is also sky trajectory of the Gaia star binary, star black hole binary. Okay. So in these cases, so this is a light ascension and declination. Only if this is a proper motion, this is a constant velocity movement like this. But due to our sort of motion with respect to the sun, it will show some kind of this wiggle or something like this. But if the object is not a single object, binary, they should have the Kepler motion that combine the Kepler motion, intrinsic Kepler motion of the system and us. Then, so this black one is the observed one. So what they really do is that the first from observation, they will just remove the constant proper motion and the effect of the Earth orbiting the sun or something. Then they are left with this kind of orbit. So they find, okay, this is the binary system. And in addition, they can see only one component of binary. They can never see any accompanying object in this particular binary system. So they conclude, so this is black hole. So this is detection. So they do a sort of follow-up of the radial-velocity follow-up. So this color, as a black line is an extrapolation or fit. Okay. But this colored dot is a real observation. So in this particular cases, from the radial velocity observation, they just have defined the binary parameters. Actually, in this case, it is quite amazing. Even if Gaia alone, their estimate of the binary parameter is very accurate. The radial velocity follow-up will just make this something like this. So I think so. This is already just good enough. In any case, conclusion is so this consists of the G-type stars about 1 m solar, and unseen companion is 10 m solar. And so this outer orbit period is 100. No, they don't say outer. So this is the orbital period, binary period is 186, and eccentricity is 0.5. So this is more than 10 m solar something. They conclude this is binary. And in particular, because of this is a projected trajectory, and if they just combine with the centricity and so some of the spherical model, they can really estimate the inclination of the angle with respect to us. So they got inclination angle with respect to us is about 50. So this is basically just a really nice estimate of the total trajectory of the system. So again, my question is, of course, in this, if this amount of mass, it is likely this to be a single black hole. Nevertheless, I can ask, to what extent this can exclude the possibility the central object is instead of 10 m solar single black hole, but 5 m solar, 5 m solar binary black hole. So this is what I really am interested in. So in this case, this particular case, this is residual. The current residual error of the radial velocity is about 1 kilometer per second. Okay? This is recently, so this is second case. In this case, this is not the main sequence. This is red giant. And again, so this is accompanied by about 10 m solar black hole. This is relatively sort of located further. And this is a sort of longer orbital period. So that unlike the previous cases, they can just observe only this one sequence of the Kepler motion. But again, so they are the same thing. And in this case, central object is red giant and very bright. So residual radial velocity error is less than 0.1 kilometer per second. That really depends on the nature of the star and the location of binary with respect to us. But so this is a two existing example. So from this, so this is a summary of the detected binary so black hole in our galaxy. X-axis is the orbital period of binary. Y-axis is the mass of the black hole. This is basically X-ray binaries, low mass X-ray binary, high mass X-ray binaries. They are very close, so they just really interact with the star and black hole. So they have some kind of X-ray emission, so this is modulation. But if this is far away, this binary content is far away, so such kind of interaction is less and less. Therefore, we cannot see anything directly emission, but simply from the motion, dynamical orbit, they can just infer the presence of black hole. They call it Gaia black hole 1 and Gaia black hole 2. So I don't know, in next 2 years or something, they should just publish a much more sort of well-documented and catalog of the Gaia sort of astrometrical observation. So some people say they will find about 100 or 1,000 black hole systems. I don't know. But it is quite likely that so at least we have 2 cases. And I don't know, well, what is the distribution of this black hole. But if some of this could be very close to us, and so this is a really mass is something like this, then I can just ask once again, if some of this could be a binary black hole instead of single black hole. So what is the methodology to identify? So this is my work. Okay. How to just unveil the binarity of unseen black hole from the observation of tertiary stars. Basically, so this is my student. By the way, this in Japanese, this is Hayashi, but in your country, maybe you got a link. Very sort of popular name, but he's Japanese, we call it Hayashi. Hayashi. This? Yes. basically, so this is what I would like to do. We cannot see anything. So if we see the binary orbit of the outer sort of stars, we could see the presence of unseen companion inside. But it could be single object or binary object. The difference is, as I showed you in the compact triple system, if we have a very precise measurement of radial velocity, or if this is outer particle or is a pulsar, arrival time measurement, there is some modulation, very small modulation, due to the presence of inner variation. So what is the amplitude of this small modulation? If we see some kind of within some signal to noise ratio, we can just really find out the inner unseen binary black holes, or at least we can put the constraint on the binarity of the unseen component. So actually, it is very easy to just very just back on the envelope calculation to estimate the amplitude of this modulation. This the motion radial velocity consists of basically three components. This is a standard Kepler motion. But if this is eccentric, this is a circular case, but this is eccentric. Due to the eccentricity, they should have some kind of additional modulation superposed on the circular radial velocities. This period is in circular cases, so this is the outer period. This eccentricity is a sort of dipole, so therefore 1/2. But this small modulation is just the orbital, the modulation frequency or period, the half of the orbital period of inner binary. So this is due to the symmetry. So basically this, and so in these cases, we can just roughly estimate this kind of scaling relative to the radial Kepler radial velocity. So this is a very small number. Basically, so this is order 1. And so this is just a ratio of the inner and outer case to the up to the 3.5. So that if, but in the case of exoplanetary system, the best of cases, we can just have the sort of spectroscopy is 0.1 meter per second. So this is the best achievable sensitivity of the existing spectroscopy. And this amplitude of E, in the case of black hole with relatively close cases, so this will be 100 kilometers. So even if we go down by 4 order magnitude smaller, in principle, it is observable. Of course, that really depends on the nature of the star and the location of the object from us. And so this is if we just do work in a little bit semi-analytically, we can just work out this. But basically, so this is what I showed. And this is basically, again, so I repeat the same thing. But so far, I just give you the result of the, if the two orbits is completely in the same orbit, coplanar cases. But in some cases, it could be two orbital plane could be inclined. So in these cases, depending on the inclination angle, then we see that this Kepler motion itself is directly modulated, because if this is inclined, the outer orbit is the inclination angle is different. So if we just see the radial velocity of the tertiary stars, due to the inclination difference, what we really observe is a sin I inclination, absolute value of the Kepler motion amplitude times sin I. If this is coplanar case, this sin I never changes. I never changes. But if this is inclined, this could be some kind of modulation. This is not a quasi-modulation. This is simply precession. If we have two cases, total angular momentum, inner and outer, is preserved. In this case, if these two does not interact significantly, simply the both angular momentum is just precessed with respect to the total angular momentum. That implies this observed inclination of the outer orbit changes. So in this case, this is a huge number times this changes. But this period is very long, even longer than the outer period. But we have to wait for a long time. But so this is completely so two different channels to identify the source signal. So this is a parameter for I do some simulations in order to do it. And actually, we do not use any secular perturbation approximation. This is a direct n-body simulation, but in this case, n equals 3. So this is a sort of fiducial parameter just to look at it. And we assume in our binary frequency, binary black hole frequency period is 10 days, and outer is 80 days. We can just change it. But if in another 10 days or something like this, this does not emit the gravitational emission time scale is about the age of the universe. So this system never merged within our age until now. So this is the result. So this is in the case of coplanar cases, as I said, this is a radial-velocity modulation. So this is a black dot is a simulation. This is a analytical, semi-analytical approximation. And so this is a completely counter-rotating cases. So this is also the case, and something like this. But if the two mass is unequal, then so analytical approximation does not work so well. But so this is something like this. So this is the case for the eccentric cases. Again, that in some cases, equal mass cases, eccentric still analytical approximation works relatively well, but unequal mass cases that it doesn't work. But in any case, so this is just a demonstration. But what is interesting is that inclined orbit. In the coplanar cases, that I think the first approximation, semi-analytic estimate works well. But so this is the case for the inclined orbit. I just give you some two different cases. So this is the Kozai effect is not significant. This is a maximal Kozai effect. These two orbits is a orthogonal orbit initially. Okay. In this case, mutual inclination between the two orbits is notice that the y-axis. This is 45 degrees. This is 44.5. Basically, this does not change. Okay. But in these cases, this is 40 degrees and this is 90 degrees. So in some at some very short distance, abruptly, that these two orbit changes about 50 degrees. Okay, so this is some kind of process, and I can just show you some kind of simulation. Okay. In this case, so basically, these two orbits is a precess with respect to the total angular moment. So this is something like this. So this is actually very critical. In this case, you can see, at some point, this is quasi-equilibrium. It never changes. But at some point, it abruptly changes something. This is a strong Kozai-Lidov oscillation, or ZKL or ZK oscillation or something. So this cannot described by analytical model. But at least this amplitude, this kind of thing that we can just really expect. If the inclination angle is small, you can have a regular precession like this. And if it is strong Kozai-Lidov oscillation regime, this is sporadic, not completely regular, but some kind of periodic. So what is the expected radial velocity modulation? That really depends on inclination to where we are, radial side direction. So in these cases, we have just from simulation, looking at the z direction, x direction, and the y direction. In general, so this could be something in between. In the precession cases, in the best cases, so this is really something like, in some cases, this is really orthogonal to our line of sight, is orthogonal to the orbit. So therefore, this is nothing. But at some point, this is significantly inclined. We have a really large radial velocities. So in these cases, quasi-stable were some cases at some point. By the way, of course, in each case is really dominated by small modulation, the Kepler motion. But end level of the amplitude is really determined by the precession or Kozai effect. And amplitude of this is 100 kilometers. So this what is the associated time scale or change of inclination. One is precession time scale. Basically, forget about these cases. Basically, both time scale is scaled by the ratio of outer orbital field divided P times P out. And in the case of precession time scale, that really depends on mutual information between the two orbits. In other cases, this additional factor will ER dependence on something like this. But just for the approximation, this could be about 100 or 10 or 100 times the P out times this ratio. Okay, so this is some kind of very approximate number for the time scale that you have to wait. Then I go back to the sort of constraint on the existing two cases. This is a constraint from shorter time modulation. In this case, you will just do maybe 3 months very well sampled high impedance observation radial-velocity. That is already done by this. And so these people got a constraint. In these cases, the residual, unknown residual, is about 1 kilometer per second. And in these cases, so this is 0.1 kilometer per second. And so if I just write a diagram of inner orbital axis of the possible binary black hole against the mass ratio of the two dynamics, this shaded region is excluded from dynamical stability. So if this in this region, so this in this case is inner orbit and outer orbit is close. Therefore, they have a very strong interaction between the two. So this system is unstable. So in these cases, if inner binary field is less than about 10 days, at least this should be stable. But in these cases, we expected 10 meter per second. So this is about 1% of the current achieved radial-velocity pressure. So in these cases, this is basically, unfortunately, these two cases, so this is, we expect a few meter per second, but observed noise of this current system about 100 times larger. Therefore, at least in this case, we cannot do it. However, but in this case, maybe I will just show you. This is a long-term modulation. And if you just wait, at least in these cases, maybe you should wait for 10 years or something. But 10 years is really short, actually. You can just measure today for 1 year, and so you can just wait for 10 years later, then you can do it. So this is quite doable. And so depending on these cases, in some cases you will have this amplitude of this. But 10 years later, this could be double or something. So this is something happens. Okay. Of course, in this case, you have to do a very precise modeling of the system. But this kind of changes are completely doable. In a sense, I say this change could be order of 10 kilometers per second. So this is very easy to do. But simply, you should be patient. And of course, you can just do anything you like, any other project. And then after 10 years, you can come back to the system. So this is quite sort of fun project. And unfortunately, I think so these two objects do not harbor the binary black hole. However, as I said, maybe in a few years, Gaia might detect 100 times more candidate of black hole. Then one of them could harbor the black hole binary. And if you discover it, wonderful discovery. So this is a quite sort of a little bit risky, but however, this is a quite wonderful opportunity for you to discover for the first time the triple system, including black hole. Nobody just discovered so far. So this is a methodology. So this is a conclusion. Now I just say that from the radial-velocity monitoring of future star black hole binaries, first we really need star black hole binary candidate. I don't have to work on it because already a few groups is working on the detection of star black hole binary system from Gaia. And as I said, they already have the two candidates. And so Gaia data is already just accumulating. So it is simply the matter of defining the parameters of everything. So just for the purpose of astrometry, they just do it. So in a sense, after the catalog is ready, some group we just do some kind of serious analysis of the existing system to find out the binary candidate. When they just publish the star black hole binary pattern, then I can just repeat all the analysis of this. Then I can just find out sort of quite likely candidate. Maybe I can just pick up only a few, for example. Then just do sort of short time scale follow-up observation. If we are lucky, we can just reveal something, even from short-time radial-velocity variation. But even if there is nothing, I don't have to give up. I'll just wait for another 10 years. Maybe if I wait for another 50 years, I'll be not in this world. But maybe my student or my collaborator, the young collaborator, can just wait. I don't know, after 50 years, some of them may not get a tenure, so they leave astronomy. But some of them are very successful getting a position. Then, just before the retirement, they will just ask their students to repeat the follow-up once again. Then if they find it, then so this is a very wonderful retirement lecture. So thank you.
Okay, we have time for a couple of questions for Suto-san. Yeah.
Yes. So I remember a few years ago, maybe 2018, there was this discovery of a triple star system to test the equivalence principle.
Oh.
Well, I was wondering if you're aware of this. And
okay, no. Actually, just, if that is the system, of course, we have to just take into account of finite interaction with a finite size of stars or something like this.
Yes.
But of course, if we have this kind of system, especially maybe that compact system, so they might do it. Because the compact triple system is much more suited to just test the gravity. Because we don't have to worry about the interaction with stellar or some interaction with the wind.
yeah, I was just wondering if this is something else you could do with this in kind of a strong gravity.
Okay, again, what I said is that if we really discover the sort of triple system, including binary black hole, this could be a very nice test bed to just do it. I agree. Just simply, just wait.
Okay, any other questions? Yeah.
So I missed that part. So I wonder, can we estimate the number of this kind of system based on our understanding of the binary stars?
It is a very good question, but no answer, because so that really depends on the formation channel for the binaries. And at least, I think maybe Sasaki-san can do it. In the case of primordial black hole triple or something, because so they can just estimate the number of binaries, then some of them might form the triple black hole or something like this. If you are interested in purely triple black hole system, maybe he can just estimate it. But in these cases, this is for, I do not, whatever reason, suppose we have a binary black hole system. Then so at a tertiary star or something like it, it could be co-evolving system, or it could be captured by accident, or if this is really close to the central black hole, then so that will also enhance the formation of that multiple system. So that kind of thing is really dependent on the theory. So in a sense, again, I could just say in completely conversely, that if we identify this kind of for the first time, then we can just really put on some kind of formation theory of that binary system. Even in the case of not a triple system, binary black hole system, there are a lot of variety of astrophysical or sort of cosmological scenario to form, but there is no consensus because this is very, very difficult. And in the case of gravitational wave emitting binary is very far away and cosmological, so we cannot do anything in the follow-up or something. But if this exists in our galaxy, if you just identify that system, then we can really continuously do some additional monitoring, so that will give you some wealth of observational information on this particular system. So this is something that I hope.
Thank you.
So I have a question about the regime that you actually excluded today. So when you have if you have the orbit, inner orbit, which is not that different from the outer orbit, therefore the triple star system is unstable. In some cases, there will be kind of a runaway ejection.
Yes.
So you will expect some high velocity stars ejected.
Yes. Okay.
And then Gaia seems to have some kind of capability to constrain statistically how often this is happening.
Again, so this is if we start with a triple, first we have to form triple. So if we have a very sort of good estimate of the sort of fraction of the triple system, then we can just apply this criterion or something like this to compute the fraction of high velocity stars or something. But the formation of triple system itself, as I said, in defined context, is a very, very challenging problem. So I cannot say that. However, I can just say the difference. So in the case of exoplanetary cases, so the planet forms maybe multiple. And some of them we just form this kind of instability. In this case, the one of the planets should naturally go out of the system. So that's the planet with free floating planet. So now people just trying to find out some kind of planet not associated with the star or something. So this is some small fraction of them are just identified. So that could be some formation path to explain the existence of free floating planet observed from gravitational lenses. So this is very different regime, but everything is very deeply related to such fundamental three-body dynamics.
Yeah. So I was thinking more like working backwards. So finding the high velocity stars first, and then try to work backward on how many candidate systems there could be.
Oh, I see. So that again, so if you have some kind of data or something like that, maybe for distribution of the velocity distribution function or something, maybe we can just trace back to some extent.
Okay. Other questions for Suto-san?
That's a simple question. Yeah, free bodies are very complicated. Is the tidal deformation will enhance your?
Yes, of course. This is one thing that very good is what I just described today is the black hole. Then in this case, most likely in this configuration, tertiary stars or something like this, not directly interacting black hole, tidal effect is completely negative. But if you have a star and black hole or something like this, tidal interaction could be very important. So that, but in this case, maybe already, so this is also inner star black hole binary interaction with any X-rays or any other cases. So this is in itself is a quite a different arrangement, quite interesting. But the talk that I gave today is so different arrangement. But again, so this is very important. So a lot of things that you can just work on.
Okay, great. Any final question? Okay, if not, I think Suto-san is around till Friday. And then, so if you want to chat with Suto-san, please just shoot him an email. And then, so we will have tea and some snacks served outside, and let's thank Suto-san again.